Well, so I want to begin, and first of all, last time, if you remember, we discussed manifolds with boundaries. And my main idea, even if I wanted to avoid it, to avoid mentioning it, is that actually we have some theory of manifolds, and we simply repeat it for manifolds with boundaries without essential changes. I want to mention some simple things which actually are specific for manifolds with boundary. And you will understand this. First, the embedding theorem. The embedding theorem that every manifold we proved in the compact case, and I said that it is true, and the proof is basically the same. In the non-compact case, just you need to consider infinite dimensional spaces, which certainly creates some difficulties. At least some seeming difficulties. But certainly this theorem can be applied to the boundary case without changes. But in the boundary case, we can do slightly more. Namely, this is actually very simple, sort of very cheap, but still, let us do it. I need some chalk for this purpose. Yes. So if M is a manifold with boundary, so dm is a boundary. Then actually we can arrange an embedding say J of M into R n minus. Now I do not specify the dimension, such that the boundary is embedded in the Rn minus 1. Actually, we can do slightly more. Namely, we can assume that the whole manifold, this is Rn minus, this is Rn minus 1, this is the embedded manifold, and we can assume that actually at the boundary points, the image of the tangent plane is transverse to this boundary, even perpendicular. Transverse will be very simple. It will immediately follow from our construction. Perpendicular requires just a little bit more work, but basically the same. So, how to do this? You remember that if we already have an embedding of M into, say, R, let me say Rn minus 1, just to achieve this. This is the same as n minus 1 functions with some properties which we discussed. This is the same. Now, if we add some more function, one or more, it will still be an embedding. And I want to add to this one more function, Jn, I will note it's H M into R, say that Jn is 0 on the boundary, negative so this belongs to R minus, negative inside, and also it should have no critical points at the boundary. So at the boundary, this function should have a non-zero derivative with respect to the vector directed inside the manifold. So how to do this? As soon as we add this function to the existing functions, g1, jn minus 1, we will have the embedding precisely with these properties. So one more coordinate, which shows that dm is still embedded in the Rn minus 1, and the interior is in the negative part. So all we need to construct the function h. And this can be achieved immediately if you use the partition of unity. Namely, you take for construction of h. Again, even for this construction, I don't need to assume that manifold is compact, but I will achieve it apply it anyhow to compact manifolds. I consider a covering of, so consider an atlas of M V alpha phi alpha. So system of local coordinates. And then in every V alpha, rather in phi alpha of V alpha, I consider a function. The coordinate xn. So in this chart, I mean open set in the manifold, we have coordinate system, and just take the last coordinate. After that, we take a partition of unity. F alpha, M into R into rather 0, 1, subordinated to the covering phi alpha of U alpha. And simply take the sum F alpha times xn. Xn is regarded here as a function on U alpha. And as soon as you do this, I have a function of the whole manifold, because where xn is not defined as a function of U alpha, h alpha is equal to 0, so everything is okay. We will have a function which obviously has this property, that it is in the neighborhood of the boundary, where we consider charts which cover, which are not disjoint from dm. Then xn is negative and has a non-zero derivative with respect to the coordinate xn, negative 1. This precisely means that the whole function will possess our properties. It will be a function which, at least in the neighborhood of dm, will possess our properties. It is all I need, but certainly I can also achieve, I can also guarantee that it will be negative inside the whole manifold. How to do that? It behaves well in the neighborhood of the boundary. Then I choose small epsilon, and simply in this neighborhood of the boundary, declare this function equal to negative epsilon, where it is greater than negative epsilon. I can make it smooth. After which I define it to be negative epsilon in the whole interior of the in the remaining part of the interior of the manifold. So this is how we can find this function, how we can embed our manifold in this way. The remaining part of the embedding theorem also can be repeated in the case of the manifold with boundaries, with all these projections and everything, and the results about dimensions will be precisely the same as they were in the non-boundary case. Yes?
Can you explain what xn is?
Xn is a function within a coordinate system, within a domain of local coordinate system. All x's, x1, xn are functions. In particular, xn is a function. Xn is a function where it is defined. X1, xn are functions on phi alpha of u alpha. They are different for different alphas, even where they overlap. And then I take this function, they are defined only within u alpha, but when I multiply this by f alpha, it will be defined in on the whole manifold, no problem. Actually, in my definition, xn will be, I didn't say this. In my definition of atlases of manifolds with boundary, the coordinate xn is always negative. Whether this domain intersects the boundary or disjoint from the boundary xn, because by definition, a chart in a manifold with boundary, its domain is an open set in Rn minus. Yes, so xn is always negative, and this construction gives you a function negative in the interior, whatever you do. More questions? Now I want to consider a construction, and you will say to me whether this is okay or we need some work to make it valid. Imagine that you have two manifolds with boundaries, same dimension, and the boundaries are the same, or at least they are related by a diffeomorphism. Understand? Oh, both boundaries are manifolds of dimension n minus 1, and they are diffeomorphic, and a diffeomorphism is given. Then I want to do the following. I want to attach these two manifolds to each other. Boundary to boundary, you understand? So I have two manifolds, M1 and M2, and M1 has boundary n, M2 has boundary N1 and 2, the boundaries, there is diffeomorphism between N1 and N2, and I just attach the point of N1 to the point of N2, which corresponds to it with respect to this diffeomorphism. What do you think I will get? I can say what I wanted to say, and then I will have additional questions. I want you to say that we will get a manifold without boundary. Like the sphere can be made out of two disks, two balls. Manifold without boundary, wonderful. But according to our definition, we do not consider topological manifolds here. We consider smooth manifolds. What about the smooth structure of this manifold? Will it be all okay? Can we describe an atlas, a valid atlas for this new manifold? Let me say yes and no. Yes, we can, but this requires some additional work. Namely, we need to construct some additional structure in the neighborhood of a boundary. And this additional structure is called a color. Now, what is this? Suppose that we have a manifold with boundary So M is a manifold. dm is a boundary. And to make it better understandable or worse understandable, I will draw a picture. So this is my manifold with boundary. Then a color is an embedding of dm times the semi-closed interval 0 epsilon into m. On the picture it will be this. If you want me, yes, you want me to give a more formal definition, this is an embedding. Actually, this is all. But being an embedding, it must have non-zero differential at every point. Here, in particular, the differential is non-zero. So this means that actually, because this is an embedding, for every point x in the M, we have x times 0 epsilon embedded in M, and this is a curve which is transverse, which should be transverse to the boundary. This is how it looks like. Such a thing is called a color, and many constructions which we are going to consider actually require some color. But the definition is clear to you. What about this definition? Do you accept it? So a color is this thing. Simply we take an embedding of dm times, I didn't say, but it is clear from my picture, that dm times 0 is met by the identity map onto dm. And then, so for every point in dm, I fix some curve starting at this point, looking inside the manifold, transfers to the boundary. And these curves together form a neighborhood of this of the boundary, which topologically is the product of the boundary and this short, maybe not very short, but I say short because epsilon is supposed to be small, usually short curve. So the picture is this. Now I want to formulate and proofs are contained in my notes. So if my proof maybe will be more pictorial then, but actually this is all very formal. Two theorems, the usual theorems, which are proved always in mathematics: existence and uniqueness. Existence is something very direct. Colors always exist. My proof actually will be valid for the compact case. Certainly what I need this dm is compact. I need this dm is compact. I do not need compactness of the whole manifold, but it is for our purposes not very important. So theorem, a color exists. What about your understanding? Do you understand what I say? Questions now? The proof of this existence is very direct. I consider, so I suppose that M is compact, although what I really need is that dm is compact, because I need to fix this epsilon, and in non-compact case, this will require some work. So, take an atlas of M. Again, at every u alpha, phi of u alpha, I have functions x1, xn, and in phi of u alpha, phi alpha of u alpha, I consider the vector field minus d over dxn. So you remember, the most obvious vector field is just the derivative with respect, partial derivatives, with respect to the coordinates. Geometrically, these vectors are parallel to the last axis, directed negatively, so in the direction where the coordinate xn decreases rather than increases, and this is for every phi of u alpha. Then I take a partition of unity f alpha and consider a vector field which is defined on the whole manifold. I take the vector field within phi alpha of u alpha, but as soon as I multiply it by f alpha, it will be defined on the whole manifold, 0 outside of some compact set which is within, is contained in phi alpha of u alpha. So this is a very much valid vector field, right? Actually, it is very easy to prove that this vector field is nowhere 0, but I don't need it. What I do need is that in a neighborhood of the boundary, this vector field is directed inside the manifold, because the coordinate xn decreases, is 0, well, at every chart which touches the boundary, the coordinate xn is 0 on the boundary and decreases in the direction transverse to the boundary inside the manifold. So we have this vector field. And as usual for a vector field, we have a flow. I erase it, but actually I will get again more of the same picture. So this is part of the boundary, this is my vector field, and a flow is precisely what we need. We take this flow, this motion at 0, we take the curves which start at the point of the boundary. So initial point of every trajectory is the point of the boundary. It is transverse to the boundary. So in some neighborhood of the boundary, this gives me an embedding of dm times 0 epsilon times some short interval into the manifold. This is the construction of a color. Is it convincing? Now uniqueness. Here I want to say, this theorem is formulated and is never used explicitly, but is always used implicitly. Because actually we have some further constructions. And always, I will use colors in this construction. In particular, this construction, which we have just discussed with you, attaching of two manifolds to each other in the case when their boundaries are the same. When we say this, we do not mention any color, as if it doesn't exist. When we construct it, we use colors, color for these two manifolds M1 and M2. And then I want to say that actually the result of this construction doesn't depend on colors because a color is unique. Even if I don't pronounce it, I mean it. So we have a valid construction. Now, uniqueness, what could it mean? Very obvious, color cannot be unique. You can imagine a different, family of curves, right? The color is unique in the following sense. Suppose we have two colors, C1 and C2. Say with the same epsilon, it is not important. We always, I didn't say this, it is obvious, we always can make the color short. We can reduce this epsilon. And I do not consider, well, so it is a possibility. So I consider two colors with the same epsilon. If we have two different epsilons and one is less than another one, then I take the smallest of them. Then my statement is that there exists a diffeomorphism let me denote this somehow, say H, of M into M, which is the identity on the boundary, such that for some epsilon prime between 0 and epsilon, this map takes one color into the other color. That is, on dm times 0 epsilon prime, C2 is C1 combined with H. So the color is unique in this diffeomorphic sense. We always can relate two colors by a diffeomorphism. In this sense, colors are unique. In no other sense. Certainly they may be different visually, geometrically. Is it clear? Now, how to prove it? I suggest a picture, and you, if you wish, can easily convert this picture into formulas. So, C1 and C2, I want to draw them. This is my dm. This is C1, and this is C2. Okay? Now, what I want to do, I will show it here. I would like, so this is x, this point is C1 of x sum t, this is C2. xt. I would like to join them by a curve in such a way that there will be a family of curves. How to do that? Certainly it is easy to do this using local coordinates and partitions of unity, but I prefer a different construction. We can always consider M as embedded. So M is embedded into Rn minus, right? Then if you take two nearby points on M, we can draw a straight interval that joins them, right? And then I want to project this interval onto M. How to do that? Let me do the following. For every point in M, again, I want to remember this picture. There is the tangent plane to M, and also the orthogonal complement. This is a plane of big dimension. My blackboard has a small dimension, and I cannot draw it a big dimensional, but this actually is, yes. So for every point in M, I have this n capital minus n minus lowercase n plane. These planes are everywhere. And in some neighborhood of M, they are disjoint. They are disjoint and cover this neighborhood. This is again a theorem from analysis. This requires the C2 class, and you know, say if you have a curve in the plane, then the normal lines certainly they can cross each other somewhere, but in a small neighborhood of the curve, they do not cross each other. And this follows from the existence of the second derivatives. I will not go to this calculus theorem, but this is true. And this gives you a projection of some neighborhood of M in R and minus onto M. When I say projection, I mean that M itself is on the M itself, the projection is the identity. But some points around are projected into M. This is precisely what I do. I take now the interval, straight interval joining these 2 points, and apply the projection to it. And I will get a curve in M. We join these 2 points. Okay? As soon as I have this, I want to repeat this picture, but maybe I will need more. Make it bigger. So this is one color, another color, right? And I have a family of curves. Well, not everywhere. This is some nearby the boundary. We join these two. Then I do the following. Let me do this. On every curve, so every curve is parameterized from 0 to 1, for example. 0 here, 1 here. I take a point whose parameter, when we move outside when we move inside the manifold from the boundary, this first it is 0, here it is 1, and here between 0 and 1. You know this function, which is 0 then 1. Same infinity function. We actually had a formula some time ago. So I do this, and I get a new color, which consists of these curves. Now everything is obvious. Because I have write on this picture a diffeomorphism of a manifold which takes this into this, just along these curves. Then we take this onto this. This diffeomorphism certainly is defined only in the neighborhood of dm, but far away from dm is the identity. Some distance here it is the identity. So we can extend it as identity to the whole manifold. And we get diffeomorphism which takes this color into this color. But if we restrict our attention some small epsilon prime, we will have that this color is mapped, one color of our two colors is mapped onto the other one. What about the construction? Believe? So colors are unique in this sense. This means, I will not maybe specify this every time, but this means that when we make some construction which uses a color, then the result up to diffeomorphism doesn't depend on this color. It will be the same for all colors, diffeomorphically. Questions? Now my constructions. Actually, I need two constructions. And this is all about manifolds with boundary. I'm not sure, maybe I will have to say something about the second of them next time. But actually, everything is very direct. First, attaching. No, the second is also attaching. But first is sort of more direct attaching. So we have two manifolds. With some diffeomorphism between the boundaries. Understand? So this is M1, this is M2, and they have a diffeomorphism, H between dm1 and dm2. Now I define a new manifold M, which is M1 union M2, with understanding that the points of dm1 are attached to the point of dm2, which are correspond to each other with respect to H. This is description of the set. Understand? Now to say that M is a manifold which contains M1 and M2 as submanifolds, I need an atlas. What else? So atlas of M. To define it, I need colors. For both M1 and M2. And the charts for M will be the following. First, all M1 and M2, they have atlases, right? M1 and M2, they are manifolds. So all charts for interior M1. All charts for the interior of M2. And more charts. These charts actually do not, charts of these two types do not cover M, because they do not cover the former boundary. So some more charts, namely, if I take a chart for dm, local coordinate system for dm, then I apply to this my two colors. So this is V, this is C1 of V times 0 epsilon, and this is C2 times V. Provided that C1 and C2 are colors for M1 and M2. And this is what? This actually, together these two maps provide a map of V times negative epsilon epsilon. I change the sign for one of them, say here, into M, which is a chart. V times negative epsilon epsilon is an open set in Rn. The map is 1 to 1, and obviously this chart is compatible with the charts of both the atlas for interior M1 and the atlas for interior M2. So in this way, I define a smooth structure over a smooth manifold, over manifold, on this thing. Now let me say something else, and maybe I will have to repeat this at least partially next time, which I will do. But my goal, initial goal, which actually remains valid, that next time we will consider Morse functions, what is called the Morse theory. But now simply I want to make two additional remarks which I can discuss with you next time. First, is so obvious, nothing to discuss. It is very possible that actually the boundaries of both these manifolds, or one of them, are disconnected. You can imagine that boundary of M1 consists of several pieces which do not know anything about each other. And this diffeomorphism actually connects not the whole boundaries of M1 and M2, but rather some components, maybe union of components. Some, as you probably prefer to say in this language, some open-closed subsets of the boundary. So if you imagine that H, actually, for example, you can consider the following. This is one manifold, and this is another manifold. Can you imagine this? So the boundary of this is one circle. The boundary of this is a union of three circles. And you have a diffeomorphism between these two, not involving this part. Then the same construction goes. And we get a manifold, we get this attaching, and the resulting manifold will be again manifold with boundary, whose boundary will be union of components of boundaries of M1 and M2, not involved in this attaching. This is something probably immediately obvious. Certainly, this construction can be made component-wise. And now one less obvious thing, but sort of badly needed. Imagine that we have the, certainly again here we need color too. Color actually only for the parts of the boundary which are involved in this attaching. But then let us consider something less obvious. Suppose that M1 is a manifold with boundary. This is M1. But the boundary of it itself is obtained from manifolds N and P by attaching with respect to some diffeomorphism between dN and dP. I write N1 and P1, please. Understand? Suppose that M2 also a manifold whose boundary or part of boundary is obtained from N2 and P2 by a similar attaching. dn2, diffeomorphism dp2. And suppose that we have a diffeomorphism only between n1 and n2. And then we can do the following. We can attach this to this by this diffeomorphism and get a manifold. Which is looked like is presented on this picture. So such an attaching, which involves only a part and not a component, a part of the boundary. This picture actually says it all. To do this, we need multiple colors. We need actually colors for both M1 and M2, plus something in the neighborhood of the common boundary of N1 and P1. But this picture says it all. What we do to attach this to this using a diffeomorphism between N1 and N2. We get a new manifold with a boundary, and its boundary, again, will consist of two parts, P1 and P2, will be obtained from P1 and P2, again, by some diffeomorphism between their boundaries. What about this picture? How convincing does it seem to you? I can say more about it next time. It will not be more convincing, but somehow you will feel that something like proof was pronounced. It is written in my notes, so maybe even we don't need to return to it. But this is a construction which will be used. Such an attaching between two manifolds with boundary using a portion of a boundary, and the portion is not a component. What do you think, Dale, about it? Does it look convincing?
Yeah.
Oh, you're generous. And you, Virgil? Yeah. You do? Probably, yes. Do it's cautious. And you? Yes. Me too. So maybe next time we will discuss it, but actually our next subject is well expected Morse theory. Thank you.